Hello and welcome to my Physics 2211 Lab 5, The Falling Slinky. The purpose of this lab is to predict and analyze the motion of a free-falling object slinky by applying Newton's second law, the drag force principle, the gravitational principle, and tension. So the overarching question is, will the slinky fall with its bottom end first? Will it fall with its top end falling first? Will it fall with both ends at the same time? Or will it fall with the top and bottom end approaching each other as it falls to the ground? So here are the general principles used and their formulas, so I have Newton's second law, and in this case, it would be the derived velocity update formula, the gravitational force, and the drag force. Onto my experimental setup, I used Tracker and imported the video to track the Y position compared with the time from the moment that the Slinky was released from the hand. And then this was then plotted on time versus position graph. In this case, the system is the Slinky and the surroundings are everything else. For my experimental observations, I found that the initial position was 0.00728 meters. And we can see that we've now answered the overarching question based on this experiment alone, that it's the bottom that actually remains stationary until the top of the slinky meets the same position level as the bottom of the slinky. From then, the entire slinky goes into free fall. This could have been seen in both the video and based on this graph. Um, and so uh, Now I'm going to go into my computational model setup. I set the mass of the ball to 0.25. That's an arbitrary number, but I set ball.pos to 0.00728, which was what we found earlier to be the initial position of the slinky, only for the y position though, because that's all that we care about. T equals 1.43 seconds because that was the moment of release of the slinky from the hand in the video, and delta t is 0.03 because that's the rate at which tracker can track the video. The gravitational constant g is 9.8, and b is for drag force is 2.6, and that was determined through trial and error in an experimental finding. For the continued computational model setup, I have two while loops. The first while loop goes from 1.43 to 5.4, and that's when the bottom of the slinky is stationary, so it's not falling yet. Um, the weight force is just negative ball dot m times g times j hat, and then tension is ball dot m times g times j hat. F net is the total of those two, and then I used the velocity update formula and the position update formula to account for the movement of the slinky. And then for the second while loop, which is while 5.4 is less than t, which is less than 10 seconds, this is when the slinky actually begins to move in free fall as a system. I have w equals negative ball dot m times g times j hat, but this time I've replaced t with drag force, which is negative b times the magnitude of the velocity of the ball squared, and then times norm ball dot vel. And then F net would be w plus the weight force. And then, of course, as usual, I have the velocity update formula and the position update formula. So some computational observations, it's very similar to the experimental observations. And we can see from this graph that we can deduce it that the slinky also starts from rest. And then after a certain point, so when the top meets the bottom, it begins to go into free fall. So now here's a discussion when comparing the experimental and computational results. So both models show that the bottom of the slinky stays at rest and then begins to free fall when the top of the slinky falls to the same position as the bottom of the slinky. However, there is an observed difference in the trajectories, and this is likely due to differences in model timing. Because for the tracker video, the video itself is actually slowed down, but the computational model does not account for this and just does it in real time. So for sources of error, well, Tracker utilizes manual tracking by clicking at points in specific intervals, meaning that the accuracy of my clicks could have varied from point to point. This could have resulted in a margin of error when analyzing the position of the object. Additionally, and this is the big one, the tracker video was analyzed in slow motion, while the computational model was coded on the basis of real time, meaning there could be discrepancies between the models in comparing time and position. So what does it all mean? How does drag influence the movement of the slinky? Well, without drag, then we would see that it's just in complete free fall, and as such, the movement would model that. However, with drag, which is what is used in real life, um, the slinky would not be accelerating completely at 9.8 meters per second squared. So what if the slinky were thrown downward? Would it make a difference to the movement of the slinky? Well, yes, perhaps the Slinky would have reached the ground faster. However, the bottom of the Slinky still would have stayed at rest until the top of the Slinky met the level of the bottom. And this shows the differences between the point particle system and real systems.